Alright, sketch the graph of each function, state the domain and range. So we'll start off by sketching it, and then that will help us figure out the domain and range. So you want to go to y equals on your calculator and type in 4 times 2 exponent, which is the button that looks like the roof of a house. And so 4 times 2 to the x minus 1. And make sure if it raises it to an exponent that you move it over. That minus 1 should not be part of your exponent. It's a normal font size. Okay, now you can graph it and look at it, but what's going to be more helpful to us is actually to press second graph and look at our table of values. Hang on, my calculator is deciding to graph. Okay, so we're going to put x and y, and we just want enough points to be able to tell what this looks like. And you don't even have to necessarily write this on your paper. So I'll start with -4. At -4, I get -0.75, -3, I get -0.5, -2 is 0, -1 is 1, 0 is 3, 1 is 7, and if I go any farther than that, I'm going to be off on my y values. So now I can plot those points. -4, -0.75 is almost all the way to -1, but not quite. -3, -0.5 is halfway. -2, 0. -1, 1. 0, 3. 1, 7. And so what we have to remember on this is our exponential function, one direction goes up, and in this case to the right, but the other direction it evens off, and there is a number we're getting closer and closer to but never getting to. And you can tell on your table of values, if you scroll more and more negative, that number that we're getting really close to is -1. And so our domain is our x values. And so if we look, my graph goes to the left forever, and it goes to the right forever. It's going to go up and to the right, but that means it keeps going to the right. So there's nothing stopping us either direction. So our domain is -infinity, comma positive infinity. But our range, which is our y values, is not going to be -infinity to infinity. Our graph goes up forever because it's going up and to the right, but if I'm looking at it going down, I don't have any values past this line, which we call an asymptote, which is at a y value of -1. So the lowest my graph is something that's really, really close to -1. The highest it is, well, there's not a highest. So we write our range as -1, comma, positive infinity. It's -1 because that's the number that it's getting really close to, but never touching. Now, number 2, to type in this logarithm, we go to y equals, and then we're going to do math, and you want to scroll up to the option that says log base. And when you do that, it gives you a log, and then it gives you a small box and a bigger box. And so in the small box we put 3, and in the bigger box we put x minus 1 in parentheses, and then we get out of the parentheses and we put -2. So math, scroll up, 3, put the x minus 1 in the parentheses, get out of the parentheses, -2, and then do second graph. And again, you might find it helpful to look at the graph, but we also want to make a table of values, and you don't have to write down the table of values if you don't want to, but here's the points I see. 2, -2, then we've got some decimals, then 4, -1, then we got more decimals, So I'm going to go ahead, and since 8's the last number, I'm going to write 8, and it's negative 0.2288. So 2, negative 2, and then 4, negative 1, and then at 8, it's just a little bit below. So to the right, our graph is going up and to the right, although it ends up going up really slowly. And to the left, depending on what kind of calculator you have, your graph may look like it stops over here. But what's actually happening is that at 1, we get an error. The line for 1 is right here. It's this vertical line. And so what happens is our graph gets really close to that line, closer and closer and closer, but never touches it. Our calculator just doesn't know how to tell us that, which is why most of our calculators stop. But it doesn't really stop. It keeps going almost straight down. And so that changes up our domain. Now our domain isn't negative infinity to infinity, because if I'm looking from left to right, well, my graph doesn't go past 1 at all. And so for our domain on these, that first value where you have an error, that is going to be the first number in our domain. And then to the right, our graph can go forever. Like, these values will keep going. If you scroll down on your table, you'll keep having more and more answers. So it's 1, infinity. And then our range, which is our up and down, our y values, well, my graph obviously can go down for forever. I can get all these negative numbers, but it also can go up forever. It's just going to go up really slowly. And so that makes our range negative infinity, positive infinity. Number 3, this is a word problem, but don't freak out about it. It's not so bad. In 1995, there were 285 cell phone subscribers in the town of Centerville. The number of subscribers increased by 75% per year after 1995. How many cell phone subscribers were in Centerville in 2002? Use y equals ab to the x. Do not consider a fractional part of a person. So we know it's supposed to be an exponential equation. And in our exponential equation, a is our initial value. So that's whatever we start off with. So in this case, in 1995, there were 285 cell phone subscribers. B has to do with whether we're increasing or decreasing and what percent we're using. So because the subscribers increased, we're going to do 1 plus the 75% as a decimal, so 0.75. And then we put our exponent out here. And so we actually can do 1 plus 0.75. So 285 times 1.75 to the x. This is our formula for it. And then to figure out how many subscribers there were in 2002, we have to figure out how far have we come from 1995 to 2002, which we would do by subtracting, which gives us 7. And so that's what I'm going to put in for x is 7. So I need to do 285 times 1.75 to the 7th power. Which gives me a lot. And so it says do not consider a fractional part of a person, which means even though it's like 0.5, we would want to round down, I would guess, because that 0.5 doesn't count as a whole person. So 14,325 people or subscribers. And I can see how it would go either way. Some people might say, oh, well, that means round up because you had 0.5, but who knows? I don't know. Okay, number 4. Each year, the local country club sponsors a tennis tournament. Play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after 5 rounds? Use y equals a times b to the x. Now, technically, it wouldn't be that hard, especially if this were multiple choice, for us just to work this out. like half it 5 rounds and then see what we get. But if we wanted to use this formula, there's 2 ways of thinking of it. Both ways has us start with 128. And then one way says, okay, I don't have a percent, so whatever I would multiply by, which would be a half, that's what's going to go in my parentheses. So that this is my equation, and then I put in a 5 for the exponent. The other way of thinking about it is like they did give us a percent, because what is a half as a percent? It's 0.5, and we're going down by that percent each time. So you do 1 minus 0.5 to the x, which gives you 0.5, which is the same actually as if I do a fraction of 1/2. So either way you want to think of it, we need to finish by putting a 5 in for x. And so we type that into our calculator, and we get 4. So after 5 rounds, there will only be 4 players left. State whether the exponential function represents growth or decay and give the percent increase or decrease. So to determine whether it's growth or decay, we just look at what is a part of our exponent, like this part right here. If it's smaller than 1, it's a decay, like this one. And if it's bigger than 1, it's an increase. Now the percent that we're increasing or decreasing, like almost all the time, like very rarely will this not be the case, it should end up being a number between 0 and 1. And so if you think about it, what do you have to do so that would we add 1 or would we subtract 1 to this so that we get something between 0 and 1? Well, we'd subtract 1. 1 minus 0.45 gives us 0.55, which is as a percent is 55%. So it's a 55% decrease. So our 2 answers are 55% decrease and decay. Decay and decrease always go together. I wrote increase here, but I meant to write growth. My bad. Okay, and so we do a similar thing here. What do I do to 1.36 to make it be between 0 and 1? Well, I would have to subtract 1 from it, which gives me 0.36. I change that to a percent, which is 36%. And since it's a growth, it's increasing. So it's a 36% increase. Now we're going to solve some exponential equations, and the general things we want to do on this is we want the bases of our exponents to be the same. So on number 7, they're both 7s, which means that negative 3v has to equal 3v plus 3. Now I want to solve by getting v on one side and my numbers on the other. So that means I would subtract 3v from both sides and get negative 6v equals 3. Divide by negative 6. And that gives me negative 1/2, which would be my answer. V is negative 1/2. So that's pretty easy, but in general, what they're going to try to do to us is make it to where the bases aren't the same. For example, this is 5 to the 2k equals 1. And so what we want to do, if possible, is we want to rewrite 1 as 5 to some power. And the question is, 5 to what power is 1? Well, it'd be 0, because anything to the 0 power is 1. And so once we write it that way, 5 to the 2k equals 5 to the 0. Now my bases are the same, so I can make them go away and set the exponents equal to each other. 2k equals 0, so I divide both sides by 2 and get k equals 0 divided by 2, which is just 0. Now on 9, I have 9 to the 2v plus 1 equals 81. So I want to try, if possible, to rewrite 81 as 9 to some power. And so if you think about it, hopefully you remember your multiplication tables and you remember 9 squared is equal to 81. So now my bases of my exponential functions are the same. They're both 9s. So I can say 2v plus 1 equals 2 and then solve. So I need to subtract 1. 2v equals 1. Divide by 2, which means v equals 1/2. You can write that as 0.5, and there was one earlier that we could also write as a decimal, but to me, since it's a 1/2, like, it's easier just to write it as 1/2, but it's whatever. Number 10. Now this one might be kind of tricky to you because now there's no way for, well, there's no easy way at least for me to say 625 to some power is 125. And there's also no way for us to say, well, that, I'm not sure I said that the right way, but I also can't do 125 to some power is 625. Like, that doesn't really work either. And so instead we have to pick a number that we can write both of them as. And so because hopefully you realize that 125 is 5 to some power, and so if you don't know what power it is, you have to guess and check. So you could do 5 squared is 25, and then 5 cubed is 125, and then 5 to the 4th power is 625, and then you actually can stop because we've got both things we want. 125 is 5 to the 3rd power. 625 is 5 to the 4th. Now it already had an exponent, and so what we do is we write that exponent next to the 4, like so. Okay, so we had to change both of them so that they'd be the same. They'd both be 5s. 5 to the 4th, and then we put the other exponent next to that, and then 5 to the 3rd. So now we write it without our bases. Now we set our exponents equal to each other. So 4 times 3x minus 3 equals 3, and then I would distribute and solve. So that would be 12x minus 12 equals 3. Add 12 to both sides. 12x equals 15. Divide both sides by 12. Now 15/12 can be simplified because you can divide them both by 3, which gives you 5/4. And so if you aren't good at that or recognizing that, remember you can type 15 divided by 12 into your calculator and then do math, enter, enter, and it will change it to a reduced fraction for you. It would tell you that it's 5/4. Number 11, evaluate each expression. You must show work to justify your answer. So we want to basically rearrange this into an exponential function or equation so that then we can figure out what it is, because this is the base of our logarithm, so it's the base of our exponential equation. Then we go in a circle. The next thing we write is the x as our exponent, and then it equals 16. So it's asking us in reality 4 to what power is 16, and that power would be 2. So this right here is the work that we're using to justify our answer. So on this one, we start with our base, which is 2, and then we go in a circle. Our exponent is x, and it equals 32. So we have to ask ourselves, 2 to what power is 32? Now that's one you might not know off the top of your head. So in your calculator, you would go through and try until you get it. I personally like to do it in a systematic way. But you're welcome to skip around and stuff if you want to. To me, that's just sometimes that can be more work than it has to be. 2 to the 5th is 32, so x is 5. rewrite each expression or equation in exponential form. So that's actually what we just did, except we're not actually having to find any other answer. I start with my base, which is 17, then I go in a circle to the exponent, which is x, then it equals the y. That's my answer. And then the same thing on 14. I write down the base to the negative third equals 18. Go the other way. Now they're giving us an exponential equation and we're going to write it in logarithmic form. So that means we need to write log. We start with our base, which is an n. Then we go in a circle. The next number is 152. And it equals our exponent, which is m. So 16 log of our base, which is a, 87 equals our exponent, which is b. Now we're going to solve each equation, and so to solve, we want to start off by getting our logarithm by itself. So I want to get log base 12 of x plus 10 by itself, which means I need to move this 9. This is 9 times my logarithm, so I divide by 9 on both sides as my first step. 0 divided by 9 is 0. If you have problems remembering what that is, remember your calculator will do it for you. And so now I rewrite this as an exponential equation in order to be able to finish solving for x. So that's going to be 12 as our base to an exponent of 0 equals x plus 10. And so 12 to the 0 is 1, because anything to the 0 power is 1. So I just need to subtract 10 from both sides. Negative 9 equals x is our answer. So we do have to check something back up here to make sure that it's really an answer. So inside of our parentheses, if I plug in that x, what matters is that this number is positive. Doesn't matter what number it is specifically, just that it's positive. So negative 9 plus 10 is a positive 1, and so that's okay. This really is an answer. If we get a negative, or if we even get 0, then that wouldn't really be an answer. So in this case, it would have been no solution, because that was our only choice. But you do need to make sure that you're staying aware of that you need to go back and plug it back in. So on 18, we're going to divide by this negative 9 to get our logarithm by itself. And that gives us log of base 8 of 5k minus 6 equals 2. And so I want to rewrite this as an exponential equation. So my base is 8 to the second power equals 5k minus 6. And so I'm going to go and do 8 squared, which is 64. And then solve for k. So I add 6 to both sides and get 70 equals 5k. So now I divide both sides by 5, which means k equals 14. Now, if I go back and look at this, I'm trying to say, is 5 times 14 minus 6 a positive number? And you may need to actually work that out on your calculator, but you also might be able to be like, well, 5 times 14 is a number that's a lot bigger than 6. So yes, this would be positive. So that's our answer. (19). So now I have this plus 9 on the side with the logarithm. So to get rid of this plus 9, I would subtract it to the other side, which gives me log with a base of 2 of 2k minus 9 equals 1. And so now I'm ready to rewrite it so that I have a base of 2 to the first power equals 2k minus 9. And so 2 to the first power is really just 2. And so I can add 9 to both sides, which is 11 equals 2k, and then divide 2 on both sides and get k equals 11 halves. And that's my answer. These next couple of problems, or 3 or 4 problems, I don't know, however many there are different than the previous ones with logarithms, because now we've got log 13 of something on both sides. And so if they're both log base 13, then what we can do is say that this has to equal this. And basically it's like we're canceling out the logarithms. And so now I can just solve this equation and figure out what k is. So I would add 2k to both sides and get 4 equals negative 2k, and then divide both sides by negative 2 and get negative 2 equals k. And that's my answer. I just need to go back and check it. Now I have to check it in 2 logarithms. So on this side, I do negative 2 times negative 2 plus 4, which is 4 plus 4, which is 8, so that side's good. And then this side is negative 4 times negative 2, which is also positive 8. That should happen. They should both be the same. But what's more important is that they're both positive. So if you work it out and you get them to be different things, like you messed up somewhere, and it's more likely that you didn't get the right thing here and need to go back. But as long as they're the same and both positive, then we're good. That's really an answer. 21, we have log on both sides, and it's not super important, but remember there's a 10 here if they don't write it. But all that matters is they're the same logarithm, so they cancel each other out. And this is 12 plus 2x equals x squared plus x. Now, it will be easier when you're solving this, because we want everything on one side. It's easier to move everything on the side that makes x squared positive, because it's easier to factor when x squared is positive. So I'm going to subtract 2x over here and subtract 12. And so I get 0 equals x squared. 1x minus 2x is negative x. Nothing minus 12 is negative 12. And so I want to factor this in order to solve it. So I'm looking for what multiplies c at negative 12 that adds c at negative 1. And I would use negative 4 and positive 3. Now I finish by setting each part equal to 0. And so I add the 4 over and get x equals 4. I subtract the 3 over and get x equals negative 3. Especially when there's 2 answers, you need to go back and check. Okay, and so sometimes it works out that both of them are. Like when I plug in a positive 4, that works out and gives me positive. If I plug in a negative 3, that's 12 minus 6, that's positive. This is 9 minus 3, that's positive. So they both do work out, but I'm pretty sure on the next one they won't. Okay, the log base 5s cancel, and so I have 3a plus 3 equals a squared minus 7. Again, I'm going to move to the right side because that's going to end up making it easier to factor if the a squared is positive. So I get 0 equals a squared. I'm going to write the negative 3a next so that it's in standard form, which is what we're used to. And then negative 7 minus 3 is negative 10. So to factor this, I want to think of numbers that multiply to get negative 10 and add to get negative 3. So negative 5, positive 2. And then I set each part equal to 0. And I get a equals positive 5 and a equals negative 2. So here's the issue. It's negative 2. 3 times negative 2 is negative 6. Negative 6 plus 3 is negative 3. So negative 2 doesn't work. And it actually gives you a negative either one of these that you plug it into. When I plug in 5, everything works out fine. They're both positive. So a equals 5 is an answer. 23, the last of this type of problem, the log base 3's cancel. Now I get 2x squared equals 3x squared plus 6x. So the tricky part on this is how do I solve it? Well, I start off by trying to get everything on one side. So I'm going to subtract the 2x squared over here, which gives me 0 equals 3x squared minus 2x squared is 1x squared plus 6x. Well, if I only have two terms, I don't have that third one, then what I really want to do is say, what do these have in common? And so they have an x in common, and if I take the x out, I'm left with x plus 6. So I set each part equal to 0, x equals 0, and x plus 6 equals 0. So the x plus 6 equals 0 means I have negative 6 as an answer. Now, if I plug in 0 on either side, I get 0. And that does not work. It has to be positive. 0 is not positive. And if you forget, try it. Do log, and you can put in log base if you want, but log of 0, it gives you an error, just like when I do log of a negative number. It will give me errors. And that's why we're having to check. So 0 doesn't really work. If I plug in negative 6, though, that does work, because on both sides the negative gets switched to the positive because it's being squared, and then we keep working it out and it works out. The negative 6 does. Now, finding the inverse of a function is really easy, or relatively easy. You just have to remember the first step is to switch the x and the y. So I'm going to rewrite this as x equals log base 6 of y minus 2, and then we're trying to get y by itself. Well, to get y by itself, we need to rewrite this logarithm as an exponential equation, and it may help you to realize this is backwards from what we've been doing most of the time. Most of the time we have the logarithm come first. So flip it around, and this would be a base of 6 to the x power equals y minus 2. Keep going. We still need to solve for y, so we add 2 to both sides. Now, this might seem tricky, but 6 to the x plus 2 is 6 to the x plus 2. Like, we can't actually add those together because the 6 has an exponent and the 2 doesn't. So they just stay separate like that. Now, 25, we're basically going to do the exact opposite. So, like the opposite steps. We're still going to switch x and y. So x equals 5 to the y minus 2. And now to rearrange this and get y by itself, we're going to have to use a logarithm. But before we do, we're going to add the 2 over to the other side so that our exponential part is by itself. X plus 2 equals 5 to the y. And again, you might want to just switch it around so that you have 5 to the y equals x plus 2, because that might make it seem more like the problems we've done. This is our base for our logarithm. This is the next part, which we're going to put in parentheses, x plus 2, and it equals y. And so that's our chapter 8.1 to 8.4 review.